Okay, I think we can start. Hello, thank you for coming to today's first presentation. My name is Andrzej Dębski, and I want to talk to you about some of my experiences of using AWS Lambda. My idea for this presentation is to show you some of the unique problems or challenges that you will face if you decide to use Lambda. And by the end of the presentation, you should be better equipped in order to assess if Lambda is actually a good thing to use for your next product, service, or use case. And if you are already using Lambda, you should be able to apply some of the techniques that I'm presenting here in this presentation to your services in order to improve customer experience. Can we show the slides? Oh, cool. Thank you. First a disclaimer. I'm employed by Amazon, but all of the opinions here are of my own. There is a link to a code, and there is a QR code that leads you to the code. Basically, it's a couple of Java Lambda handlers that I'll be showing, and a CDK code that you can deploy to your AWS accounts so that you can play around with examples if you want. For Q&A, you probably know that we are using Slido, so just use the QR code or just go to the web page, input the hashtag, and you can input your questions, and I'll answer them at the end. So a little bit about me. I have around a decade of experience working with Java language, or generally JVM platform. I also did some commercial work with Scala for a couple of years. Mostly I was writing backend services or products, a little bit of front-end, but yeah, mostly backend. And in terms of my experience with Lambda, I've been using it since February 2021. This is when I switched teams in Amazon. And the team that I joined, they already had two services in production running on Lambda, so I helped to maintain and extend them. But I've also created two new products/services that were using AWS Lambda. So I had a chance to see how one goes from like the ideation phase to designing the technology and then actually rolling it out in production. In terms of the things I want to talk about today, so there are three topics I will cover. Number one is this thing called cold starts. I want to first explain what they are, and then go a little bit deeper and tell you why the JVM, it makes things even worse for cold starts, and then show you some of the common techniques or approaches that you can use to minimize their impact or suggest ways that you can get rid of them altogether. Then I want to talk a little bit about costs and try to answer the question, is AWS Lambda expensive or not? And in order to do that, I'll explore a couple of scenarios where I'll compare the costs of AWS Lambda versus something like AWS Fargate, so a more traditional approach of deploying software. And then at the end, I want to talk a little bit about caching, specifically in-memory caching, and why some of your, let's say, ideas about in-memory caching and expectations, they won't really be working as you expect if you decide to use them in Lambda-based services. So, cold starts. Probably some of you already know what that is, but I'll start from the basics and then we'll build up on that knowledge. So, to understand cold starts, we first need to talk about the Lambda lifecycle. So basically, like initially, like you write your code, you have your handlers, you somehow deploy it to AWS, either in an S3 bucket or like a zip archive, a container, whatever. So the code is there. Lambda knows that, hey, there is this function and there is this code, but nothing is running up until the first request is sent to your function by the clients. This is when AWS Lambda knows that, hey, this is the request that I need to handle, so I need to spin up an instance of the function in order to handle it. So this is where the init phase comes in, because every instance of your function needs to be initialized. And there are two things happening. The runtime is initialized. In our case, it's a JVM, like AWS spins up a JVM somewhere. And then our function needs to be initialized. In case of Java handlers or like Java functions, it means that Lambda takes our function and executes the constructor of the handler class, and also things like initializes static variables, executes static blocks, and so on. So already from that, it means that the more things we do in the constructor of our function, the more clients, some of the clients will wait for the requests to be handled. Because from the point of view of the client, they've sent a request to your Lambda function and they are just waiting. They don't know what's actually happening. Now, after the function has been initialized, the request handling can start. So this is when your handle method is invoked and your business logic is executed. And this is where the JVM comes in. Because some of you may already know that JVM does a lot of things in a lazy way. So, for example, your code, your classes are loaded only when they are first encountered during the execution. So during the first invocation, a lot of the things are happening because your extra classes are loaded. Like probably you don't have all your business logic in a single class. You use some dependencies. All of that needs to be loaded in memory, and that will happen on a first request. Additionally, JVM, or like the Java compiler, Java-C, doesn't really optimize, doesn't really perform a lot of the optimizations with the code. So it's not doing, there isn't an option like with GCC or G++, like -O2 to optimize our code. The Java or JVM will optimize your code on the fly by gathering runtime telemetry and this sort of information. And only after obtaining that information, the code will be faster with more executions. So this is another type of cold start, where the first couple of, or like first n requests, they will be slower, but with time they will get faster. So that's why on JVM, the cold starts are even worse, because they not only affect the client waiting for the init phase to finish, but they will also affect the clients during the latency will be impacted because the JVM will optimize things along the way. So there are two types of cold starts. Type 1 related to init phase and type 2 related to JVM. And also to make things worse is that Lambda, a Lambda instance or one instance of your function can only handle one request at a time. So let's look at the example. We have one client and they make a first request to your Lambda. So AWS Lambda, like the AWS service, it creates a Lambda instance. And the invoke number 1 waits for the init phase to start, to complete, and then for the request and the request starts to be handled. But if the client then, for whatever reason, invokes the same function again with a different request, another Lambda instance will be created because a Lambda instance can only handle one request at a time. So this means that this client, like both of the requests of this client, they had to wait for the init phase, and they are going to be quote unquote impacted by the JVM being slow initially. So the impact of cold starts on your client's latency, it not only is a function of how many requests your Lambda function is getting, but how many requests at the same time need to be handled. So now let's look at some examples and some timings to see, like, how bad is that cold start? Like, is it really bad, or is it something we can just ignore? So for this, initially, I'm going to use a very simple Lambda function. I'm just showing you this. That's just a bunch of code that will be executed during the function init phase. So we have a constructor, we have some static variables, but nothing fancy. We are just initializing a logger, taking some measurements. Like normally constructors in actual services are much more complicated and time-consuming. So for the initial test, I've written a very simple Lambda function. So the business logic just accepts the input. It in a JSON format, it gets one of the fields, sees if the number is even or odd, and prints that information. So very simple, like trivial business logic. Yeah. So I've deployed this function configured with 128 megabytes of memory. And the memory in Lambda is important because when you deploy Lambda, when you configure a Lambda function, you only control the amount of memory assigned to it. There is no separate configuration for, hey, give me 256 megabytes of memory and 4 CPU cores. That's not the way it works with Lambda. With Lambda, the amount of compute power you get for your function scales with the memory. So the more memory you assign to your function, the faster the computation will be. But this is quite a small Lambda function, so I just went with 128 megabytes of memory. I've deployed the function, and I've made 4 requests in around like a 15 minutes window time. So the first request, we can see that there is both duration and init duration. Both of those values are reported in CloudWatch logs, so you can get them like out of the box for all your Lambda functions. So the init duration, this is the, if you see for your Lambda instance an init duration reported for a request, it means that this request had to wait for the function instance to be initialized. So this is basically the cold start type 1. So the runtime init and the function init. So we see that for even this very simple function, the init duration is almost 2 seconds, or like 1.8 seconds. It means that the client, like the client altogether had to wait almost 2 seconds for the request to be served, because the Lambda had to be initialized, the Lambda instance had to be initialized, and then the duration itself is like 85 milliseconds. So yeah, the duration itself, it may be fine. It's quite fast, but the init duration is really big. It's like orders of magnitude bigger than duration. So that already gives us information that the cold start type 1 can have a very big impact on our latency, especially on the tail latencies, or basically we can see spikes in our latency graphs because of that. Then I've made some additional requests, and we see that there is no init duration because Lambda tries to reuse existing function instances if possible. So Lambda reused this already running function instance, and because the code was already loaded, the JVM JIT started to work its magic. The duration is like 2 seconds. It's nothing. It's quite fast, especially like in a standard like business scenarios. But then we can see that the 4th request, done around 15 minutes since the original one, it again has both the init duration and the duration. So that is an example of Lambda just recycling or killing off running containers after some time. We don't have basically any guarantees that Lambda instance that was created will live for example, 15 minutes, 30 minutes, 1 hour, 2 hours. Lambda doesn't give us any guarantees. Based on anecdotal evidence, the function instances, they should live from like 15 minutes to 1 hour. But still, like this will also influence the number of cold starts that your clients will experience because Lambda just recycles the containers. So now that we've seen some example timings for cold start type 1, let's look at what's the influence of cold start types 2. So here I've deployed a little bit more complex Lambda function. So here I've just tried to make things more real life. So I have an if-else, and in one branch versus the other, I'm using different libraries. So in the first branch, the 1,000 random numbers are generated, and then some math statistics are calculated using Apache Math library. And in the second branch, I'm using Jackson library to deserialize the whole JSON into my class. This is basically trying to emulate a situation where we have multiple types of APIs in our services, multiple paths in our code that use different libraries and different code. Now, let's look at the timings. Here, I will ignore the cold start type 1 / the init phase, because this isn't something I want to focus on. Instead, I want to focus on just the duration. And I've had to deploy this Lambda with 256 megabytes of memory, because JVM was complaining that I wanted to load too many classes into too small amount of memory. So there are 3 requests. The first 3 requests, they are to the code path number 1. So the one with the math calculations. We can see that with each subsequent request, the duration goes down. So as we expect, the first duration, the first request is the slowest one by like orders of magnitude. That's because the the Lambda, when initialized, it needs to load our class, needs to load our classes, it needs to load some of its own classes, and so on. So it's quite a lot of work involved, one-time work involved during the first request handling. Now, the second request, we already see that there is a significant speed up. And that's because the code is already in memory, maybe some like pre-optimizations were done. But like we can see the trend of each subsequent request is faster. And the times will converge to some number. Now, what happens is that I've made a request to code path 2. So the code path with the Jackson library. We now see that there is a big regression in terms of the duration. So the duration, again, goes up to 1+ second. And that's because, an entirely new set of libraries had to be loaded. Because in the code path type 1, in the code path 1, we didn't need to use Jackson libraries. So JVM didn't need to load them. But here in the code path number 2, it had to load those classes in memory because that's the first time that we are using them in that function instance. And probably or maybe Java JVM JIT is quite smart, and sometimes it makes assumptions that, hey, I can see this code, but it's not actually being executed, so I can simplify some of the things. And so if the JVM already did some very deep optimizations, they may need to be rolled back, and it also takes time. And we can see that a subsequent request to code path number 2, again, the time goes down because stuff is loaded in memory. So we can see the pattern where if we have different requests to our service, depending on the timings of requests, our latency graphs can look different, and we can see anomalies. And this is actually something that I've experienced in one of the services that we were maintaining, that we've seen occasional spikes in latency. And after investigating it, it turned out that most of those spikes were caused by the first request to be sent to already initialized Lambda handler, but it was executing less common code path. And that caused the duration for this request to go up. And I'll talk later how can we protect ourselves from such situations. So now that we know what are the cold starts and what can be the impact on the client's latency, let's talk about what can we do to try to minimize the impact on the client's latency. So number one strategy is to use something called provision concurrency. This is something that is usually recommended if you read AWS documentation. It basically is a feature introduced in Lambda some time ago, where during the deployment configuration, you can ask Lambda to keep a given number of your function instances already after the init phase, or quote-unquote warm, to execute the requests. So basically, you will have a pool of functions that have already been initialized, and they will be first to serve the customer requests. So for example, if you ask for 5 provision concurrency, as long as you have less than 6 requests at a time, they won't be impacted by the cold start type 1. The downside of this is that it's costly, because normally in Lambda you only pay for the function executions. So you only pay for what actually is needed. In case of provision concurrency, there is an extra charge for keeping the functions idle but warm. So this is breaking this serverless on-demand promise a little bit, because we are still being built for something that is ready to serve requests, but it's not actually doing anything. So it's just it's cheaper, but it's something like just paying for servers that wait to handle the traffic. The second option, and this is something that was used before the provision concurrency was introduced, is create a stream of background traffic. So the idea here is that we have this stream of dummy requests that we send to our function, and we hope that those requests will trigger or will keep enough of Lambda instances up and running already to serve requests, or to serve production requests. This is a best effort because you don't have any control over the routing in Lambda. So you may have situations where that dummy requests, they are handled by already initialized Lambda instances, And the production requests are unlucky, and they will actually need to wait for the new function instances to be initialized. So yeah, this is a best effort and something that people were doing before the provision concurrency was introduced. And the number 3 approach is basically use a different language. Because if you look at some comparisons between Lambda using Java or versus Lambda using, for example, Go, it turns out that the cold starts are greatly the cold starts on Java are quite large compared to other platforms because of the runtime and because of the fact that the code in Java is not really optimized before its execution. Alternatively, you can use GraalVM. There are blog posts about it. I've linked one of them that show you how you can do this. It's not applicable to every Lambda function, obviously, and GraalVM has its own set of drawbacks. But it's an option if, in your case, you really care about latency, but you don't want to rewrite your Lambdas to a different language. It's an option worth exploring if you don't want to throw money at the problem and add provisioned concurrency. So I will focus a little bit on provisioned concurrency, given that it's a recommended way to solve or mitigate the cold start problem. So as I've already said, in provisioned concurrency, you basically ask the AWS Lambda service to keep a number of your functions up and running, or like number of instances of your function up and running. So one trick that you can do to reduce both cold start type 1 and type 2 is to add code in your constructor that will basically execute your business logic with some dummy inputs, so that A, the classes are already loaded in memory, and B, the JVM JIT already does some of the initial passes. It obviously increases the time it takes to spin your new Lambda function instance. So some may argue that, hey, if the client is unlucky and the request will be handled by on-demand Lambda, it will take even longer for the function to initialize. So what you can do is, again, add a little bit more code and actually detect in the constructor if a given Lambda instance is executed as provision concurrency or on-demand Lambda. And if it's on-demand, you may just decide not to do this pre-execution of some of the code paths. And this is actually like trying to emulate something that is also very common in server-based environments, where once you want to add a new server to your fleet, you start it up, start the process, and then send some requests to your server before adding it to your load balancer. So again, you already have a server that can handle the traffic that's already been that already did some of the work, and some of the things have been initialized. And now let's look at some again timings. So I've basically deployed the same function from the previous example. So the one with 2 cove paths, one with the math calculations, and the other one with the Jackson library deserialization. And I've added this code that basically executed both cove paths for sample inputs. So we can see that again, the first request overall to our Lambda function, it's slower than other requests, but it's still like 33 milliseconds versus the number that we've seen previously was 700 milliseconds. So we already see that we see a significant improvement in the duration of the first request. The second thing we can observe is that after the first request, the duration or latencies are quite consistent. And that's because both cove paths have already been executed, for example, inputs. So we don't have the problem of, hey, this is an entirely new cove path. I need to load classes right now and have the client waiting for it. So yeah, as we can see, the provision concurrency allows you to mitigate quite a big impact of cold starts. Some of the best practices for provision concurrency. Number one is the provision concurrency is configured strictly not for a function, but for an alias of your function. An alias is basically like a different name for your function. It's a different ARN. And this is important because if you already have Lambda in production, your clients will be calling your function using the function name or function name IRN. So even if you add the provision concurrency and it's configured on an alias, if you don't update your client's code, they will call your function and you won't actually get any benefits of provision concurrency because it's configured on an alias. And this may seem like a silly error, but I've seen it happen a couple of times that like people configure provision concurrency, didn't update their clients, and they were confused why they don't see any improvement in latencies. So just keep that in mind, that you will need to update your clients if you have them. Number 2 is AWS CloudWatch gives a nice set of metrics for Lambda and for provision concurrency. The most useful ones, in my opinion, are spillover invocation, tells you how many requests to your Lambda function could not be handled by provision concurrency because there were not enough like provision instances, and that's due to the number of like requests being sent at a time. So for example, if you have 2 provision concurrency and you need to handle 3 requests at a time, the spillover invocation will basically be 1 every like second or something like that, depending how often you get requests. So we can monitor how many requests basically are impacted by cold starts or like they are impacted in a worst case by cold starts, and then you can make a decision if it's fine if, for example, 10 requests are impacted, or you may want to provision more provision concurrency. The second metric is utilization, and that gives you information how many provision concurrency instances are being used. And interestingly, you can even configure auto-scaling policies on that. So you can auto-scale the number of provisioned function instances, for example, based on this metric or some other metric, or maybe during the day you have more traffic, so you already pre-provision automatically more instances if you want. So yeah, like we are back to auto-scaling our services, even on Lambda. The third thing is use this trick of pre-warming your code paths in constructor so that the less frequent requests, they don't need to wait for the classes to be loaded and so on. And the fourth thing is you can use code deploy with Lambda and use code deploy deployment policies so that if you use provision concurrency, you deploy a new revision of the Lambda, the code deploy will gradually shift the traffic from the old revision to the new revision while also shifting the provision concurrency capacity so that you don't have a situation where you deploy a new revision, you switched all the clients to the new revision, but provision concurrency is still being like moved from the old revision to the new revision. So to recap, cold starts really affect the client's latency of your Lambda functions. And depending on your use case or your service, it may be fine, or it may be something that you need to really think about before using Lambda, or you may really need to think about in terms of how to optimize them. You can accept the various types of cold starts if you are using JVM. If you want to mitigate them, again, you can use provision concurrency as the default solution, but you will need to pay for that. And the last one is, it's a very generic that you should like monitor metrics and add instrumentation to your code so that you know where the bottlenecks are and which parts you will need to optimize to get the best results. So let's talk about costs. And as I've said, I want to try to answer the question, is AWS Lambda expensive? But it's hard to answer that in a vacuum. So I will focus on some of the scenarios just to give you some kind of idea when and if and when it may make sense to not use Lambda due to the costs. But first, a recap how AWS Lambda is priced. So for on-demand Lambdas, you are billed for 2 things. One is this unit of gigabyte seconds, and it's basically the sum of time that your functions were actually running and handling requests times the allocated memory. So you say, give my functions 1 gigabyte, and the more memory you will give to your functions, or the more memory you will allocate to your functions, the bigger the bill will be. And you will pay for each invocation. Like the single invocation, it's very, very, very cheap. But if you have like billions of invocations per month, it will add up. For provision concurrency, it's a little bit more complicated because you pay for the same things. You pay for the execution of the functions, you pay for invocations, but you also pay a separate charge for keeping a set of your function instances quote-unquote warm and ready to handle the requests. And it's basically the same thing. It's a sum of the time your functions are waiting to handle the requests times the amount of memory you allocate. And the other thing that it's worth remembering about Lambda is the free tier. So the free tier gives you like 1 million invocations free per month and 400,000 gigabyte seconds free per month. So you get this monthly allowance of free compute and invocations for on-demand Lambdas. And it's a quite good thing to remember because sometimes you may want to build something that is not really invoked very often or is quite modest in terms of the resource requirements. And if you deploy it on Lambda, it may be very, very cheap to run, especially for like processes around testing and just gluing things together. Okay, so how can we calculate AWS costs in general? So there are multiple ways, like you can do it by hand on a piece of paper, you can do it in Excel if you know the formulas, but one useful tool offered by AWS is AWS Pricing Calculator. It allows you to create like scenarios where you say, I'm going to use this, 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 and that. I'm going to use this for that amount of time, for this amount of requests, and so on. So you basically define the usage scenario. And AWS will give you a cost estimate per month, but also it will give you a very nice breakdown of how were the costs calculated. So you can actually understand, hey, in my estimate, maybe the storage is the most expensive part, or maybe the networking is the most expensive part. And then you can start thinking if that actually makes sense, or you may want to optimize. And the other thing is that you can then share the estimates and the calculations using the links. So it's a nice way to prepare estimates, look at them in detail, and then also share them, and then discuss them with your colleagues or like including documents and so on. So this is just a screenshot from the cost estimate AWS cost calculator that I've used to make my estimates, and basically it shows you that there is like a very nice breakdown, for example, for Lambda. Oh, this much for compute, this much for invocations, and so on. So in order to actually calculate costs, we need to make some assumptions because we need to know some things. So number one is I've assumed that average request time is 200 milliseconds. That's just because I had to pick some number. I will focus on monthly costs because this is something that AWS pricing calculator gives us. For region, I've used prices from US East 1. There are different prices in different regions, but they should be similar enough so that the conclusions we draw from one region, they should be applicable to another region. And the last part is I will just focus on compute cost. So how much we would pay for Lambda or Fargate. I will ignore things like network egress and things like that. So I've considered 3 scenarios. Number one is just hello world Lambda function that is getting a constant stream of requests. That will give us a baseline numbers that we can then see how we can see how expensive is Lambda in like a very simple scenario. Then I will compare Fargate with Lambda because from my experience, teams are very often thinking, should I deploy to Lambda and use serverless, or should I deploy Docker containers to Fargate and just have things like quote-unquote servers. And in the last scenario, I want to try to do some very simple calculations in how much would it cost to run the Stack Exchange network of sites, think Stack Overflow and others, on Lambda or Fargate, just to see some real-life scenario and calculations for it. So the hello world scenario, we won't focus too long for that. It's basically a function that would receive a constant stream of 1 request per second. And that in a month gives us like 2.3 million of requests. And I've assigned 256 megabytes of RAM to that function. So we can see that on demand, it's like relatively cheap. It's less than $1. That's because a lot of the compute was quote unquote covered by the free tier. So we don't really need to pay a lot of money. For provision concurrency, we can see that it's much more expensive compared to the on-demand because we pay for A, because free tier doesn't cover provision concurrency, and B, we pay for keeping the functions idle, and then we pay for actually running them. So we see that there is a difference, but like even still, like running something for $5 a month, like some people may say, oh, it's cheap, I have some guarantees, like I have some better guarantees regarding the latency, I'm going to use that. Let's move on. So now let's look at the Fargate example. So Fargate, as I've said, it's basically an AWS service where you can deploy Docker containers. And there are two let's say, variations. One is that you will deploy them on your EC2 machines, or the other one that you just ask the AWS to provision some kind of task with a given CPU and RAM assigned to it. And I focus on the second scenario, where we just give Docker container to AWS and ask for a given amount of resources, and it will create a Docker somewhere, and it will be available to handle the requests. So for Docker, for Fargate, I've used the smallest task size, so 1 virtual CPU, 2 gigabytes of RAM. And for Lambda, I've assigned it 1,769 megabytes of RAM. And I've already said that in Lambda, the compute power scales with the amount of RAM. And according to AWS documentation, this amount of RAM should equal to 1 vCPU compute power. So it's more or less apple-to-apple comparison in terms of the, let's say, compute power. Yeah. So we can see that Fargate is the most expensive one and most expensive option, but I'll let's say dive deep on that price in a second. We can see that on demand and provision concurrency, they are again, there is a difference, like 4 times difference between those prices. And it makes sense, like with provision concurrency, we pay for both keeping the functions idle, and then we pay for handling the requests. We don't have the free tier. Yeah. The interesting thing is that someone can say, oh, Fargate is more expensive than on-demand and provision concurrency. I will not use that in this scenario. But we should remember the difference in terms of like what Lambda and Fargate gives us. Because in case of Fargate, we have this task, we have this Docker container that can handle requests. And a single Fargate task can handle probably like tens or hundreds of requests, depending on like the networking and this stuff. And the compute price will be the same, because in Fargate, we pay for CPU and RAM. We don't pay for the number of invocations. Where with Lambda, if we would increase the number of requests per second to 5, the price would automatically increase, because the functions would be executed more often, and we would have more invocations. So one Fargate task can handle like more load using the smaller price, but there is a little bit of operational overhead. And we also need to think about that in case of Lambda, the AZ outage scenarios should be handled more automatically for us, because let's say one AZ goes down in AWS, and AWS will just start spinning the function instances in different AZs. Where in Fargate, it may mean that the task has to be brought down and reprovisioned somewhere else, and it may take longer time, depending on your specific task and Docker container. So now let's look at a real-life scenario that we can calculate. So all of us know Stack Overflow site, and it's part of this network of sites called Stack Exchange. And Stack Exchange is basically a collection of Q&A sites for different topics. They're like Unix, books, cooking, English, and so on. Nice thing is that folks at Stack Exchange, they publish their traffic statistics. So I went to the site and I've obtained the information that they handle like 1.3 billion of requests, or like they have 1.3 billion monthly page views. And assuming a very simplistic scenario that we have the traffic is constant throughout the month, we get around like 495 requests per second. So for Fargate, I wanted to go with the assumption that I want to handle AZ outage scenario. So I will provision 9 tasks, but only 6 tasks are required to handle all the load. So that gives us like 82.5 requests per task, which sounds okay, reasonable. And then for Lambda, my calculations assumed the most expensive scenario. So the scenario where we want to handle every request with provision concurrency. So we know that we have 495 requests per second. We are going still with the assumption that we have 200 milliseconds request time. So if we divide 495 by 5, we get 99, and that gives us we need 99 provision concurrency instances to handle all the traffic, assuming this very simplistic scenario. Okay, so now the numbers. First thing we can observe is that Fargate now is much cheaper option than both the Lambda on-demand and provision concurrency. So that already gives us information that, hey, there is this point in our service, there is the amount of load where the price of Lambda doesn't really, or like the ease of use of Lambda may not justify the high cost compared to other compute platforms like Fargate. Because again, with Fargate, we have our 9 tasks. We pay for the tasks, we pay for the resources, but we don't really pay for each invocation. And also another thing interesting is that provision concurrency is cheaper than on-demand, which is not something we've seen in the previous examples. And again, it's because of this very specific scenario where we assume that Lambdas are working constantly. So there is no basically, we don't actually pay for this idle time where the functions, where provision concurrency functions are waiting to handle the requests, because they are handling the requests all the time. And the cost of handling, like gigabyte second of handling requests for provision concurrency is actually cheaper than on demand. So again, there is the point where we may see a situation where provision concurrency is actually cheaper than on demand. But like every case is different, and one needs to run the numbers and see if that's the case. And like I was very surprised by this difference in the price in on-demand and provision concurrency. So I just like plotted this very simple graph where I've taken the formulas from the cost calculator and try to see where is the, let's say, the point where on-demand, the blue line, is more expensive than provision, the red one. So for example, for Lambdas with 1 gigabyte of memory and 200 milliseconds request time, at around 64 requests per second constantly, the provisioned Lambdas will be cheaper than on-demand. Not by a lot, but if we stick with Lambda and our traffic grows and grows and grows, the difference will be also continue to increase. So a quick recap. Number one is remember about the free tier for Lambda. If you are not creating like a live request reply service, but you want to have some kind of a component that glues other components together, like reads something, does some computation, saves something, and it's not really invoked in a month too often, or is very, it's not very resource, it doesn't really require a lot of memory. Lambda is a nice option to implement such a component, because the monthly costs should be relatively low. You should use AWS pricing calculator if you want to use AWS in general, or you want to try out and you want to see how much a new service would cost you, because it's a nice way to make some initial calculations, and it will give you some kind of a mental model how expensive a given service is. With more traffic, the Lambda will get really costly. So if you're thinking, oh, I will have a service with 1,000 requests per second, I would advise you to run the numbers and see if Lambda really makes sense from a cost point of view. You should take advantage of the free compute during the init phase for on-demand Lambdas. That means that when your function constructor is executing for on-demand Lambdas, you are not paying for that execution. So you can, maybe you have some pre-computations that you want to do for every Lambda instance and not change it for the lifetime of that Lambda. You can move that to the constructor, and it will increase the init time, but you may save some money. For consistent workloads, as we've seen, the provision concurrency may actually be cheaper than on-demand Lambdas. So it's worth running the numbers. And the last thing, and the last point, is that when evaluating a technology, we should think about the total cost of ownership. So it doesn't really, like, even if Fargate is, let's say, cheaper by $100 a month, maybe it doesn't really make sense to use it because your team already is familiar with Lambda. So always keep that in mind when making a final decision if you should use one technology versus the other. Yeah, so caching. Before I go straight into the problems with caching on Lambda, I want to explore like this evolution of a service that I've seen a couple of times. So we start with a very simple case where we have an EC2 instance or instances, we have the business logic, we have some data store, we do reads and writes, like data store can be DynamoDB or like relational database. Everything is fine, but you know, there comes a point where we want to decrease the load to database or we want to improve some of the latencies. So we usually decide, oh, let's add a cache. And usually it's just an in-memory cache that is like a separate instance on every server. And you know, this is a very common pattern where you have a cache, you first check the cache. If the information is there, you return it. If it's not there, you go to the data store and you have some update strategy. After some time, you decide that, hey, like it doesn't really make sense to lose all the cache information during the server restarts. You really don't, or you may want to avoid a situation where all your servers go down and they need to be brought up and they have cold caches and the latency is unacceptable. So usually what you do is you add another layer of caching. You can call it L2. And it's out of the process cache and it's something like Redis or like any other like cache that lives outside your server instances. It complicates the architecture. The flow is more complicated because we need to console the in-memory cache out of the process cache and data store. But still, it's quite a common thing to happen to services that want to improve some of the latency characteristics. And the problem with caching in Lambda is that this L1 cache, the cache in memory, it may not give you the same benefits as you would expect from a server-based environment. That's because in Lambda, we've seen that Lambda instances are very short-lived, 15 minutes, for example. So it doesn't leave a lot of time to fill out the caches and to benefit from that cache hit ratio. Because sometimes before the cache gets filled, the Lambda will just throw away your function and the JVM, and the new ones will be started. Another one is you can't really implement the asynchronous like updates in the background. Very often people have, oh, I have this cache and I have this thread in the background and it does some bookkeeping and cleaning and updating from main data store. In Lambda, when your handler is not actually handling requests, it's frozen. So even if you spin up another thread, it will only execute when the function is executing requests. So you might have a situation where the main thread is executing the requests, it returns the result, and the async, the background thread, doesn't really have time to actually finish its work. So you basically don't benefit at all from this pattern. And the third part is you don't control routing in Lambda. You can't tell Lambda, hey, send the requests from this client to this Lambda instance if possible, where if you have a load balancer that is smart enough, you may have some kind of a sticky session algorithm where you try to optimize so that the requests from the client, they try to go to the same server if possible. And what can we do? Number one is if you want caching and you want the good results, unfortunately, you probably will need to have this out of process like L2 cache, like Redis or something like that, just because the Lambdas are recycled very often. You can add L1 cache. It's not that it's not possible, but you may see a lower performance / cache hit ratio from those caches than you would expect from a server-based environment. And the third approach, and it's a little bit complicated, is you can use Lambda extensions. It's basically another layer of code that can execute alongside your code. And there are some even AWS services that use AWS extensions for caching. I have an example in the code. I won't go too deep into that topic because it's quite advanced and not actually used very often. But yeah, you can explore it if you need better caching in Lambda. And that's basically it. And we can go to Q&A because I think we have a couple of minutes. So I will open the Q&A site. And if you want to go to a Q&A site, you can scan the QR code. Okay. So there are two questions. Please describe your best practice for dev, UAT, prod, CI/CD, local development testing. Yeah. So this is quite problematic sometimes for teams using Lambda because you deploy your code to AWS And sometimes you may not even be able to run it locally. So in terms of the dev, I think it's important to have some kind of a quote-unquote main function that you can actually run your Lambda locally. There are also like libraries in GitHub that try to emulate some of the AWS environments in your local like laptop or like computer. So this is something that it's definitely, if you decide to use Lambda, you should definitely invest in this kind of tooling and think about the development workflow before deciding to use Lambda. UAT, I guess it's user acceptance testing. So in my case, like most of my work was either like a super backend service where it's an API, or we were developing things for Alexa. So basically, we tried our best so that, for example, every developer has a copy of their like function and can actually route the request from their Alexa device to their own Lambda, so they can actually test the whole thing from beginning to an end. It required some time and thinking, but it really paid off because the developers were really productive and they could actually test things before like pushing the code and waiting for it to deploy. And in terms of CI/CD, yeah, like most of my recommendations will be the things that AWS recommends. So basically, like we have multiple stages in our deployment pipeline. So we have like alpha, beta, prod, and for every stage we deploy to different AWS accounts, and we have a suite of tests that run both. They both invoke our Lambda, just using the Lambda API, but they also invoke it from like outside, trying to emulate the customer flow. Yeah, and in terms of testing, we just use standard JUnit tests for like quick testing, and we have some integration tests that basically invoke our Lambda using the Lambda APIs, so they invoke the function from outside. Yeah, like if you are interested in this topic, I would recommend you to read. There is this like set of papers called AWS Well Architected Framework. It's like if you search on Google, you will find it. Not all of it is applicable to Lambda. Some of it is basically development practices in AWS. But it's really nice to at least read about how like big companies do it, and some of the suggestions that are really applicable, I think, to every team. Okay, let's move on to the next question. Will the minimum build time be lowered anytime soon? Because why pay 100 milliseconds if request just takes 5 milliseconds? That's a very good question, and that actually happened, I think, 1 year ago. Right now, the billing resolution is 1 millisecond. It used to be 100 milliseconds, but in one of the re:Invents, they actually lowered it. So yeah, I agree. It doesn't really make sense, and it's a solved problem right now. It's 1 millisecond resolution. Yeah. Will Lambda be terminated even if it's being permanently used? So your Lambda, if you have a function instance and it's executing a request, it won't be terminated as long as the request finishes in 15 minutes, because that's the hard timeout for Lambda. So if you have a request and the Lambda is processing it for more than 15 minutes, the execution will be stopped. But the Lambda container won't be recycled if it's executing a request. Yeah. So as long as your requests are executed or like handled faster than 15 minutes, then no, you won't have a situation like in spot instance where the spot instance may be taken from you. Fortunately, that's not the case. And that's all of the questions. So thank you very much for your attention. If you have any other questions, like feel free to grab me and I'll be happy to discuss them. Thank you.